Whoa, it's Kat. It's good to see you again. Howdy, howdy, everybody. Welcome in. As y'all come in, please do hop along and sign in to this check-in thingamajiggy. Oh, that's so valid. I admittedly haven't really been on well, at the GHW thing since like last year. So it's been a little bit for me too. Awesome. We'd love to see it. So, as new people hop into the chat, feel free to keep on propagating this link. I am actually going to also share another link, and that'll be the link to the workshop material for today. There's gonna be lots of good stuff on here. I'm using it as kind of our pseudo slide deck, but also as like a drawing board. You won't have access to this today. We're going to be doing just I guess like a give me some ideas in chat and I'll be populating on here sort of deal. But yeah, I'm gonna have a bunch of links to all of the things that inspired me for this. The link is not clickable. Oh. Well, are you able to I guess like do the oh, you know what? Even better, I'll just post it in the Discord on the announcement. Please wait while I do that. Okay, there you go. You should have access to it now. Okay. Yes, I can. How's that? Ooh, congrats on the amount of channel points. Dedication right there. Okay, so welcome to the thing. I think before we get too far in, I want to just quickly set some expectations for what this is going to be. We're all going to be here to learn, and when I was in school, I didn't spend enough time, I guess, like building fun projects. So today we're going to be building some fun projects, or at least one. And so we're going to be playing around with the genetic algorithm today. So it's going to be a lot of live coding sort of deal, and a lot of geeking out about the coding chain, which is where I got most of the, I guess, like practice and resources from. And if you are trying to redeem like Twitch points, I don't know how to do that. So yeah, we're gonna get things moving and kind of introduce what a genetic algorithm is. So basically, it is the synthesis of a few things, but the big picture is that it kind of simulates, I guess, like evolution and mashes that together with computer science to solve problems, specifically sort of like optimization problems. So I have like a little excerpt that I co-wrote with GPT to kind of like help paint this mental model a little bit. And here it goes. So basically, if you can imagine we had an infinite number of monkeys typing away on typewriters, kind of like the infinite monkey theorem. Imagine that like they're trying to, I guess, like type things away and okay, let me take a step back actually. The infinite monkey theorem, if you aren't familiar, kind of states that if you have infinite amount of monkeys and infinite typewriters, eventually they will one day recreate the entirety of Shakespeare's works. And it is a excessively like really small possibility that happens because Shakespeare's works has a lot of characters, and each of those characters have at least 26 options. So it's a bit of a problem. TSP problems as well. Nice. I don't know what a TSP problem is, so feel free to elaborate on that in chat. Okay, so but going on, where was I? Oh yeah, so right now, like if you were to just like brute force that, I guess it's a really funny theorem because it talks about the idea of like brute forcing people into making recreating the Shakespearean bits. But if you give them like a little bit of help, I guess like by grading them, then you could get them to recreate Shakespeare's masterpieces a lot faster. And so if we were to kind of start grading them and combining these scripts that were doing pretty well with other scripts that were doing pretty well, then you end up with a much better, I guess, like solution. And so out of all of the, I guess, like machine learning models, I really like this strategy probably the most, just because like it's easier for me to create like a mental model and try to like understand what's going on. Um, Okay, you know what? That's a fair point. Infinity, at infinity, a lot of possibilities do occur. It is really funny to also just imagine like an infinite number of monkeys. Okay. Anyway, let's keep moving. So the kind of like order that we like to go about in writing a genetic algorithm looks something like this. I'm going to be using P5 for today. That is the same tool that our boy Dan Schiffman, the guy who does the coding train, and like who wrote like a super cool book, which we're going to be taking a peek at later, does use. He uses the P5 thing. I'll show you guys. Sorry, I'll show everybody. So this is his textbook, completely free textbook. The link is going to be in the whiteboard if you want to get your hand on a copy of this thing. All right, see you, Kat. Thanks for dropping by. Yeah, I really want. Okay, I invite you guys to be checking out, I guess, like the sources that kind of like made all these things. For now, we're going to start off by taking a look at these things, and then we're going to kind of decompose the P5 example and just kind of like break it down into the different like component parts, so that it's easier for us to structure our own project. Okay, so but first off, I think it is important to kind of, I guess, like explore what P5 is. So real quick, I am going to go to editor.p5.js. So basically, it's P5 is a JavaScript library and allows you to kind of like create things like this. And so the one that the example, the genetic algorithm example that I want to show off that is related to the infinite monkey theorem and created by Dan himself looks kind of like this. If y'all can see that. And so we can see all of the different like generations of like to be or not to be kind of strings kind of populating around. And we can see that there's some like total stats right there. So if we were to kind of like take a look at how this example was structured, it will help us kind of, I guess, like go through the rest of this process. Yeah, Brave is really nice. I like the built-in ad blocker. Okay, so the way that Dan might have gone about this for the problem statement is, let's see, might have structured it something like this. I want to generate a quote from Shakespeare with random characters. That's random characters. And let's see, we could. Well, I guess this is very basically what it is that we're trying to do. So now if we were to go into the parameters and think about what it is that we can, I guess the numbers that we can play with are. Let's take a look at this. So the things in a string, wow. I'm not sure why I didn't rehearse this. I probably should have rehearsed this a lot better. I'm going to take a step back and we're going to go back to the order of things that we need to, I guess, like define. we'll need to be creating I guess, like a population of like entities of the things with random traits, because that's how we, I guess, like in evolution, um, it doesn't happen with just like one thing. You have to have like a population of things, and all of these things have to have like, I guess like there's this like concept of like DNA, which is like you're kind of encoding. What's the best way to describe this? Maybe I should have just like copy and pasted a definition of what a genetic algorithm is. Let's see how the textbooks does. They are inspired by genetics and evolutionary theory, and here we go. Okay, so it implements 3 of the core principles of Darwinian evolution, which is heredity, which is in the sense that, I guess, like the parents of these entities can pass down their traits to their children, and then there's variation, wherein the children can be different, and that's where the randomization happens, and then selection, which is where we figure out which of those children, or like, I guess, like entities ended up being really good. There we go. Okay, so when we go about, I guess, like planning out our own genetic algorithm, we'll need to, I guess, like define the fitness of our elements, I guess, like all of these things. So if we were to do a quick code tour, we've got a main sketch, we've got a DNA sketch, we've got a population sketch, and I made a lettuce sketch to kind of like populate where the things that we're going to be making are. I guess like we'll talk about that later. So we've got these 3 files. So if we were to look into DNA, this is the thing that kind of, let's just take a peek at it. So the very first thing is there's a character selector over here. That's kind of boring, so I'm just going to hide that. If we were to take a look in here, we can see that this constructor is basically just creating a DNA sequence. And so this DNA sequence is just kind of going to represent it's going to be representing the characters that we use in our string. So that makes sense. It also has like a fitness variable, which we will investigate in a little bit. We've got this thing that just says get phrase. That's kind of boring, so we're gonna skip that, or we're gonna hide that. We've got this thing that's called a fitness function. And so the fitness function is what determines like who's going to survive the next generation. And so this one is just doing a little bit of math to see like how many of the characters in the string over here actually match the string that we're looking for. So that's how they calculated the fitness here. This is the crossover. So basically this is the mixing between the parents to create a new child entity. And then the mutation rate is, I guess, just the amounts of characters that get randomly regenerated to have like a gene mutation. So this is how you get the variety in the thing. So if we see here, as long as the number is less than the mutation rate, then it will replace randomly one of the characters with a new random character. Okay, cool. So that is the DNA. Then if we were to take a look at the population and break this down, there's a lot going on here. So let's just start from the top. We've got this constructor, a bunch of variables, and I think the most important thing to pick up here is that the population just like generates a bunch of new DNA strings. Okay. Then we've got a fitness array. So basically it looks like it's just going to go ahead and score each of the strings and see how good of a fit they are. We've got natural selection. So this is basically just going to say the ones that had a higher I guess fitness are going to be more likely to reproduce. And the ones with the lower fitness are going to be less likely to reproduce. Okay. Then we have the generation. This basically just does all of the meta stuff of, I guess, like mutating and then like spawning in a new population. Get best returns, it's just a getter. Evaluate just grabs the most fit member of the population. That's another getter. That's another getter. This is a getter, but this is for the average fitness. All phrases. I believe this is just for printing it out. Okay. Now if we were to look at the, I guess like the driver code, we can see that there's a function here, setup, and a function here that is draw. These two are mandatory functions inside of P5. So basically setup just runs once at the very beginning, and then draw runs every time, I guess like after that. Most of this is just like boilerplate for actually, I guess like printing out the rest of this over here. Okay, so now that we've kind of taken a peek at that, I'm going to go back over here and let's try to fill these things in. The parameters that we're kind of changing are just the strings at each index and the chars, characters at each index of a string. I see you guys are having fun with the laser pointer. DNA encoding is just straight up the string, the DNA string. Okay. We've got the fitness function components. So this just means what is it that we're measuring, and these are just the, I guess the characters of the string. And then the fitness function itself is, I guess it's like how many characters are correct in the correct space. Like Wordle, kind of. Okay. So now that we've kind of taken apart what one of these, I guess like a genetic algorithm kind of looks like, it's time for us to design our own. So if you've seen me in a previous stream, I guess it's been a while. So hi. The main thing is, okay, a little bit of an inside joke, but we were kind of memeing about lettuce in my first stream, and so I'm just going to keep on going it. All of the Ryans are in on this. So I'm going to keep on going with this lettuce theme, and we're going to make some sort of lettuce themed problem, or I guess like project in P5. So this is where I'd like to ask y'all for help with coming up with, I guess like what kind of problem we should be, I guess like what kind of example do y'all want to see themed around lettuce. I kind of did some thinking about this, and I thought that we could kind of bring things around to either being some sort of lettuce ecosystem where the things that we're selecting for are the lettuce traits, or we could do some sort of like a greenhouse optimization where we're trying to figure out like where the lettuce should be, I guess like sort of planted. So go ahead and drop in chat like what it is that y'all would want to see. I guess to make things easier, why don't we just like, I don't want to put up like a I don't know how to do that in Twitch. We just go ahead and type in chat, like whether you want the ecosystem or whether you want the greenhouse. Who is head of the lettuce club? Head lettuce. That is a fantastic question. The head of the lettuce club is the person who eats a head of lettuce the fastest in a lettuce eating competition. If you're still in university, you should check to see if your club or if your university has a lettuce club. That's part of the lettuce enthusiasm. Okay. Let's see. What are we looking at? How many votes do we have? We have 1, 2, 3 for the greenhouse. And we have 1, 2 for the ecosystem. And I think I just saw another vote for the greenhouse. So it looks like we're going to be building a greenhouse optimization problem. So the next thing is for us to kind of like figure out what our problem statement is going to be. Like, what is the thing that we're going to be making? So I think this is a good time for us to use our good friend ChatGPT to come up with some. Will the Ryans be competing online soon? That's a fantastic question. We don't currently have a lettuce eating competition planned yet, but I'm hoping that when I get enough like support for the lettuce enthusiasm within the MLH community, we can eventually get together and do some more lettuce themed things. Okay, so hi chat GPT, or I guess hi Copilot. This is Copilot. Let's give it the context. I'm writing a genetic algorithm sketch in p5.js, and I'd like to theme it around. Should be a mini game. Are you talking about the genetic algorithm thing that we're doing today, or are you talking about the lettuce eating in general? Okay, so I've opened up the chat thread with Microsoft Copilot. Let's see what it comes up with. It's a lot of stuff. No, the water bottle is empty. Well, I don't know if you're talking about my water bottle, but I know my water bottle is empty, so yeah. Ooh, a lettuce minigame. It would be funny if we were able to do some sort of I guess like mini stream for MLH, where all we do is we just like everybody just grabs their a head of lettuce and is like prepared for this, and they just eat it along with whoever's running the stream. Okay, so back to the topic on hand. we've got 10 different options. What's the best way for us to... You know what? I'm going to just highlight this, grab that, pop it into the whiteboard. Now we've got options. Okay, I'm also going to paste this in chat. These are the options straight from ChatGPT. Oh, you know what? I just realized that it would have been way easier for me to just share the chat thread, because I think there's a way for us to... Where is this? To just share this entire thread, isn't there? Huh. Oh, maybe not. I could have sworn there was a way for us to share chat threads. Dimmer? Yeah. Yeah, I haven't... I need to go find out what happened to Dimmer. It's been a little while. Okay, anyway, we've got 10 different options for, I guess, like, setting up our problem space for today. So go ahead and drop in chat, I guess, like, whichever optimization problem that you'd like to see solved. Or if there's something else. Optimizing a watering schedule. Okay. Oh no, wait, so Dimmer had to leave? Oh, that's so sad. Well, I hope that his new job is treating him well. I guess it's only fitting that I would find out about Dimmer from Twitch chat. Or I guess YouTube chat. For those who don't know, Dimmer is another like MLH streamer who runs a lot of these streams. Sounds like he's no longer able to do, I guess, like this side job of MLH coaching. Okay, so we've got one vote for watering schedule. So I'm gonna go ahead and start figuring out something for that. So first thing I'm gonna do is I'm actually going to go back to chat and say, I like the watering schedule idea. And let's see what chat comes up with to give us a head start. Okay, so we've got all these variables to consider. These are the things that we're going to be trying to optimize. Okay, time of day, irrigation method. Oh, it already gave us some starter code. I've had very mixed results in copy pasting a lot of starter code. Let me know in chat if you guys want to see that, or if we should try to do this ourselves from scratch. for now, I'm gonna just start importing these things over to our whiteboard doc. Move these things to the side over here. Very good. Frequency of watering. The amount of water. Time of day. Irrigation method. Okay. Almost forgot to add in the problem statement. Let's see what the problem statement was here. I'd like to optimize the watering schedule of my lettuce garden. Using a genetic algorithm. Okay. So as far as our parameters go, the variables that we play around with, I think those would probably do well like being directly encoded. Actually, I'm not sure if I didn't do enough thinking to find out if we actually needed to have like a dedicated thing for this DNA encoding. So I'm gonna just chop this out, and if we need to define that later, we'll bring that back. The fitness function components. When I was initially drafting up, or I guess like rehearsing this workshop, the previous example that I was playing with actually needed the fitness function to be broken down somewhere. So we're gonna just like go ahead and simplify this a little bit. Okay, so I think one of the really important things for us to try to figure out in the planning stage is we should probably try to figure out what the fitness function is. And then I think we're gonna be spending some time trying to figure out how to model, I guess, the rest of the system, the rest of the simulation. Okay, we got a vote to do it from scratch. Sounds good. No GPT code here. Okay, so as far as this fitness function goes, we need to figure out how all of these variables might be scored together. So what we can do is ask chat, can you come up with a fitness function using the variables to consider for this problem? A bunch of this code stuff. Okay, so you know what? Why don't we actually take a look at the parameters that we have and just look at what the target parameters should be for a lettuce thing. Oh, nice. Wait, I want to see what it is that it's going off of. Water usage efficiency. Ah, that is another parameter that we should be adding. So I'm going to go ahead and add that to the whiteboard. Actually, no, that would be part of... I guess that would be a fitness component, huh? Okay, I'm going to bring this back. Fitness components. We want to be able to measure water efficiency. I guess like Yeah, water efficiency, maybe like lettuce health. I think those are some good ideas. Soil moisture. Honestly, yeah. You know what? Let's just roll with these fitness function components, and then if we need to adjust it later, we'll adjust it later. So I'm just actually going to do it in the same order that they did it. Soil moisture levels. Water usage efficiency. Okay. Fitness function. Nothing too crazy. Looks like it's the waiting times. Actually, I'm too lazy. I'm just going to screenshot that so that we can get to the actual fun stuff of actually coding this thing. Okay, so now that I have the notes up, let's start actually planning this thing out. So in P5, the first thing I like to do is I actually like to make this canvas the entire size of this window over here. So we can do that with window.inner width, window.inner height. Run that, now it fills the entire screen. Okay, cool. Let's see. Oh, you know what I forgot to do? I forgot to plan out what this thing should look like in our actual sketch. So we've got our text editor over to the left, but what is it that, how do we want to arrange this? Probably want to put like the stats of the thing maybe up here in the top half of the screen. And then what is it that we want to see? Maybe we can just like have a grid of plants. Like this. And so each one of these has like a different, like it's like soil thing going on. I guess as far as the stats go, we'll probably want to be keeping track of the individual fitness components. And then maybe we can highlight, I guess, like the lead stats at the top of whatever the best generation is. Let's see. Okay, yeah. Maybe we'll just like leave the stats up here, and then we'll have like a little lettuce thing going on. I'm gonna get a better shape for that. Here, we're gonna say that this lettuce is star-shaped. Okay, so we'll just have like a grid, something like this. So I actually went ahead and already have some grid code. So if we were to run this, we've got a nice grid here. I'm gonna go ahead and yoink this, paste it over here. We're going to run print lettuce lines, run this puppy. There we go. Okay, that's just my compulsive control saving. Okay, so I guess what we've done here is we've just like made 4 sets of lines, divided the whole screen up into 16 squares. So the next thing for us to do is actually start, I guess, like trying to I think the next thing for us to do is to actually start modeling what the lettuce is going to look like. And then once we have like a lettuce thing, because like I guess like displaying and representing how the simulation is going to work, I think is a really key component of actually making sure that the genetic algorithm works. So we're going to spend some time figuring that out. So let's just make a new function. We're going to call this spawn lettuce, or actually let's call this draw lettuce. And so let's see. We've got, what were the different variables again? I'm gonna just plop them up here. Oh, it doesn't have the thing. Okay. We've got soil moisture, plant health, water usage. So we need to find a way for us to represent this. To make this more, I guess, like reusable, let's go ahead and make it so that we can plop in an X and a Y in here. And we'll start by making a draw lettuce call over here to somewhere in the middle of the screenish. Actually, let's just start in this top left corner over here. So we'll just start off with 0, 0 as our origin point. So in P5, we can just do this and spawn in some text. I'm going to go ahead and do this. Spawn in a leafy green. By the way, if you are on Windows, the shortcut for spamming emoji in a text editor is Windows plus the period button. Okay, so if we run this, we've got a lettuce that kind of popped off over the top. So let's bring that down a little bit. If this is going to be our lettuce, we actually want this to be, I guess, like halfway between this whole thing. I guess like in the middle here. So I'm gonna add in some more parameters. Let's also add in the width and the height of the box that we're working in. Okay, so that for us to actually plot where this thing's going to be, let's see. We want this to be in the middle. This is going to be x plus w2, and then y plus h2. That should put it halfway in the middle. It didn't. What is going on? Was expecting a third parameter. I didn't add in the width and the height of each of these boxes. Let's see. What is the best way for us to yoink this? Maybe we just do this, and then I actually drop off those arguments. Still kicking a fuss. That's because I deleted those things. Let w is equal to... Actually... Okay, so now we've got a small lettuce in there. Let's go ahead and size that up a bit. I think it's font size. p5js.org/reference. Text size. Let's give it a nice size of about 20. Okay, it's a little bit off-center just because the point of origin seems to be the bottom left. I think I actually did another sketch, a practice sketch here. Yeah. That was able to figure out a good ratio for this. Maybe, you know what? I can just copy that. Let's see how different that is. Okay. So right now it's actually spawning in the top left corner. We want it to be more in the middle. And I think it's easiest if when we give it coordinates, we just give it coordinates that are referring to the top left of each box. Da, 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 da. Let's... TS was text size. Let's also add in Glad you think this is cute. I gotta say, I really love the Microsoft emojis art. Like, I think it's just so cute, and I think being able to use emojis in art is a pretty funny thing sometimes. It makes it feel a little bit fancier. I was actually teaching some creative coding at a local high school, and we were using P5 to do all of this. And one of the sketches that we did was using emoji painting to, I guess, like teach about like mouse events. Let me see if I can actually pull that up. I should have it somewhere. Okay, so this is the sketch that I was referring to. Basically, it's exactly what it looks like it does. You can just like paste a bunch of emojis everywhere. If you want to play around with that, I'm just gonna drop that in the chat. But yeah. Anyway, back to this stuff. Where were we? We were adding in this. Well, this is getting kind of hard to read down here, so I'm going to actually grab a couple more variables. Let's see, let x offset be 0 minus ts divided by 2 plus box. X is width. Let y off is equal to z0 minus, nope, plus ts4 plus box h. Okay, then this allows us to just very simply have okay. Oh, okay, cool. I think that is a bit too much. Oh right, we forgot to divide this by 2. Okay, there we go. Now we've got the lettuce in the middle. The circle's not moving because we didn't add the offset here. Whoop. Ah, right. Well, honestly, we don't really need a circle. I was messing around with using a circle before because I was trying to, when I was doing some practice for this, I was trying to figure out whether or not we should try to demonstrate like the amount of personal space each like kind of lettuce needs. So I was toying around with getting the circles to, I guess, like perfectly hang around like out there. So that's what this practice sketch was actually. So if I were to actually hide this, if we were to click in here, we can see that I was able to actually get the circle and the emoji to kind of be somewhat centered. And I figured out the right proportions for this, because if we were to go into here and change the radius to like, I don't know, like 300, the ratio is still roughly the same. The thing is that means we need another variable here. But honestly, I don't think we really need the other circle in here, because we're just going to put in probably some text for each of these little cubicles that's going to explain, like, I guess, what were the parameters that we had again? Oh, it's going to describe what the fitness components are for each of one of these things. Although it would also be useful for us to maybe put in some information on what, I guess, the frequency of watering, the amount of watering, and whatnot as well. I don't know. We can try playing around with which one we actually plot on the thing. For now, let's just get rid of that circle. We don't need that circle here. Yeah, there we go. Maybe we can visually represent like how much the frequency of the watering and whatnot with like little rectangles at the bottom or something. Make it like a little bit of a game UI kind of thing. Okay, so I can just yeet this because that is all done now. So we've got our little lettuce thing. Cool. Okay, so the next thing for us to do is we need to figure out the maths behind, I guess, like each of the fitness components, because we've got the soil moisture, which is affected by the frequency of watering, amount of water, times when watering occurs in the day. Irrigation method. I think I'm going to scrap the irrigation method because I feel like that's going to be kind of hard for us to model in P5. So let's start with these things. Actually, before that, I think it would be good if we can start drawing this lettuce stuff in all of the cubes. That way we know that each of these things, I guess, like their own entity. Because right now, when we're drawing these lines, oh yeah, I guess this is just a background line, so we don't have to worry too much about that. What we need to do is we should probably populate a lettuce thing in each of these cubes. So the way that I like to, I guess, like work this out is I like to just start hard coding the first few examples and then see how that kind of, what the numbers look like. So I know this right here is 0, 0. And then I know that this right here is going to be the box width and the box height. Let's see. Maybe what I can do is I can actually abstract this. Not abstract. Take it out as a global variable up here. Whoop. Let's just see real quick if that's still running. That's not running anymore because of this. No. Box is used before declaration. I thought this was going to put it into the global scope. I'm really getting skill checked by a basic JavaScript problem. Okay, we're going to leave that back in there, and we'll just make a another set of variables that do the same thing for now. Okay. So if we were to write this in terms of boxes, we'd probably do box W times 0, box height times 0, box W times 1, box height times 0. Okay. So if we're able to do this, we should also be able to do this. Okay. So this is row, this is the column. So for let's do the whole row. Row is less than, well, it's only 4 across. So we're just going to do 4 row plus plus. And then in here, we're going to have a nice nested thing going on. We can probably start at 1. No. I was thinking that was thinking of something else. Da, 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 da. Times row, times call. Let's hide these and see if that generates. Awesome. So now we've got a lettuce in each of these cells, which is pretty rad. Now we have to do a little bit of research to figure out how much the frequency of watering affects the plant health. I guess we also have to define, like, how are we going to model plant health? What did chat say about plant health? Leaf color, size, and overall plant vigor. Okay. I think we're just going to say that however big our lettuce is how healthy it is. So we're just gonna say size, and this is going to be the visual indicator of fitness. Okay, and then for water usage, I guess we should also make some sort of visual indicator for this, just to make it easier for us to see what's going on. In P5, you can use the console, but like actually using the canvas is so much nicer. So I'm gonna keep on, I guess, like trying to do as many things visually as possible. So let's go ahead and have another function. It's called draw water. I'm gonna give it a x and y, and let's see. I guess we could just use a nice like rectangle maybe. Do y'all think we should put the water indicator maybe like standing vertically or horizontally, or maybe do you think we should bring back the this circle and have the radius of that be the indication of how much water we're using? Let me know in chat. We'll call this volume of water as far as the units go. For now, let's just try running along with a rectangle. So in P5, whenever you're using shapes, the first 2 parameters of like any shape is generally the location. So we're going to try to stick along with that. And then the next 2 for a rectangle is the width and then the height, I believe. We can always double check that like this. do. Okay. Let's go ahead and draw some water here. We'll do this at box W times the column. That's going to just draw the water directly on it. So maybe let's subtract this by... No, we should do the offset in here. No, the offset's already done specifically for the lettuce. So if we were to run this again, yeah, there we go. We got a rectangle that's covering up half of the screen. More than we need. Let's bump that maybe to 30. Let's just make this the we'll make that for now. Later on, we'll probably be passing in another variable here. That's just like the water volume. For now, actually, you know what? Let's just go ahead and pop that in. Water volume. Lettuce fitness. Let's just set this at, what's the current font of our lettuce? It's whatever TS is, which is R divided by 2, and R is 100. All right. Let's just call this fitness. We'll set this to be at 100. Anywhere that we see R, we'll just turn this into fitness, which is only once. So if we run this again, it broke again. What's it saying? You may have accidentally written water. Ah. Draw water. We did. Water volume. Now we got some other problem. We received a nan. It's because we didn't actually fill in something here. That is fitness. Okay, so now we've got something to indicate the amount of water and whatnot. I keep on control saving. Not logged in. Gotta remember that. Okay, so we've added those in. I'm gonna just get rid of that because I don't like clutter on the screen. Hide that. Hide this. Hide this. Now for us to actually get into the genetic algorithm part. Oh my, I did it again. So, I think we should start by defining... Oh, I'm trying to make a folder. Create a file. dna.js. Okay. So we're going to make a class that's called DNA, and we need to implement a few things. We need to implement... Gotta go back to my notes. A constructor. We need to implement crossover mutation. We're going to leave the selection stuff to our population class. Let's see. What else do we need? I'm going to take a peek at the example. We need to calculate the fitness. Yes, this is true. Whoop. Calculate the fitness. Selection, we'll save that for population. Oh, I'm looking at the wrong file. Get phrase. Calculate fitness. Crossover mutation. So yeah, we only need a calculate fitness. Okay. So what are the things that we need to measure? The variables that we're trying to optimize for are, let's see, this dot frequency. Let's just initialize this to 0. This dot quantity. This dot timing. Okay. Let's see. Time of the day, the amount of water. No, the amount of times we fill up water, the amount of water, and the timing. Okay. So the next thing is for us to, let's see. I'm trying to figure out like where we should add in the logic for like how much water is like spent throughout the day and like, because like when it comes to figuring out how these values are going to change, we need to look at how water and lettuce interact with each other. But I'm trying to figure out if we should do this right now or if we should just figure out the rest of the genetic algorithm stuff. I'm feeling like we should just do the rest of the genetic algorithm stuff. Cause yeah, we could start calculating the fitness here. Okay, so we know that the components of fitness are the moisture levels. Let's see. Should I add that to this? Let's for now add that in. We're gonna call this SML. PHI. We're gonna give that a capital so that we remember that it's a acronym. WUE. Okay. There we go. Calculating the fitness. The biggest thing is this is going to, I guess, like return or we basically need to somehow convert these values into something that we can do here. Or sorry, into this. No, actually, soil moisture has a direct effect on the plant's health indication. This is just a way for us to measure this stuff, what the current thing is. So I don't know if that's so much of a component as it is like a median, like a variable that sits in between the indication and the variables themselves. Okay, let's do a little bit of research, shall we? Let's try to figure out maybe like what the rate of evaporation for water is at different times of the day. I think 9 a.m. is a fair time. So we're gonna start there. Yeah, it depends on a lot of things. Let's see if there's a calculator that does this for us. Humidity ratio of saturated air. Velocity of air. What? Okay. This is in meters squared. So let's try to figure out how much space a head of lettuce takes. Six to 18 inches in meters. Nope. Okay, well, we know it's how much is 18 inches in meters. 0.45. So this is on the upper end. Maybe we just round this down to 0.4. 0.45. We'll call that 0.45. Let's see what it says. It says it needs more information. The maximum humidity ratio. Let's just yoink that value here. And let's yoink this value here. And let's yoink that value here. Wow, that was like really small brain of me. I guess all I needed to see was that the equation itself was just like they're just multiplying everything together. Okay, so we know that the evaporation route is 0.0045 kilograms per hour. So let's just put that somewhere in here. Kilograms per hour. Okay. So the next thing is we're going to need to figure out how many kilograms. I guess we could just measure how many kilograms of water in a liter. Yeah, it's 1-to-1. Okay. Good to note. Good to remember. Okay. So we've got an evaporation rate. I've just realized that we actually need to figure out if that evaporation rate, like how much that changes. So we just use this one. We should be consistent. The values were 0.2, 0.15, 2. Then it was what? What did we say? It was 4.5. Whoop. Okay, so let's see. Maximum humidity ratio of saturated air in the morning. What does this say? Some common temperatures. So let's see. We could. Well, I'm based in San Diego. So I'm going to base this the humidity ratio off of the San Diego weather. And let's see how that goes. So, San Diego weather. Let's assume it's Wednesday so that we get the nice this hour forecast. So it's going to be 71 degrees Fahrenheit to 72. And then it's 80 degrees at the hottest. So I'm going to put that down somewhere over an hour. Whiteboard. 9 a.m. it is 71 degrees. 12 p.m. it is 80 degrees. 9 p.m. it is 72 degrees. I do like looking at the 6 a.m. and 6 p.m. thing. Maybe, you know what? I'm gonna make it. We're gonna do 6 to 12 to 6. Then it's like a 6-hour block, and nobody waters at night, like at midnight, right? Plus, those numbers are a lot crazier, or a lot more interesting to look at. So now we just have to convert this to Celsius. Fahrenheit to Celsius conversion. We got a nice 66, which is 18. We'll call it 18.9. Okay, that's in our whiteboard. What about 80? That is 26.7. Then we've got 76, which is nice, 24.4. Okay. I don't remember what I was doing with this information. Oh, right. Now we plug this into the table. So I'm gonna go ahead and yoink this, paste it into there. We cite our source. Okay. So 18, we're gonna round that up to 20 just so we can get the saturation pressure of 0.16. 0.16. And then the other two, let's see. Did I get the right number? If we're rounding this to 20, then this is 0.14. We'll call it 1.15. Maximum humidity ratio. The current ratio of air. This is getting really annoying to try to figure out. Why don't we just like... I don't know. This might be a little bit scandalous, but I kind of just want to just like give some dummy evaporation rates. Because I feel like this is getting a little we're getting a little distracted here. So let's just say that if we do 6 a.m. What's the 6 a.m. is equal to 0.045 kg per hour. We'll call this 0.7. We'll call this one 0.6 kg per hour. Let's run that to 5. Okay, so now we can model the evaporation rate of the water. We're going to need to probably have like some sort of a helper function for us to figure out how moist this water is going to be. Let's see, because we've got frequency, the watering, we've got the timing, the quantity. I guess frequency and timing are going to be related, aren't they? I'm going to remove the timing from our model for now. And let's see how far we can go with the more simplified optimization problem. Let's see. So I'm going to just assume that we're running with evaporation rates of this much. Is there a way? Whatever. .05 kg. I get a little into commenting the code sometimes, so don't mind me. Okay, so now that we have the evaporation rates, we can try to figure out the... Where am I? I'm getting lost in my own thinking right now. We need to figure out how the frequency, quantity, and the moisture levels are related. So a big thing is probably trying to keep the moisture levels within the right threshold. And so the frequency and quantity is going to be about making sure that we stay within that threshold. So how much, let's see, how much water does lettuce need? Watering every 4 to 5 days. Inches of water per season. .23 centimeters. I don't know how long a lettuce season is. Where are your numbers? 1 to 2 inches of water per week. There we go. We'll call it, okay, so we've got a range of 0.15 to 1 gallons of water. Let's convert that to liters because I think the math is easier to do that way. Gotta cite our sources. Toss this into the whiteboard. Gosh, this is kind of like haunting me because like I just want to be like doing all of the fun like visual stuff, and the genetic algorithm bit, and right now we're spending a little bit too much time on the modeling the actual thing. Oh, I don't know if we're gonna finish this in time. Let's do our best. Okay, we've got an evaporation rate. Let's see. We've got the moisture level target SML. Let's call it that is 0.5 to 1 gallons. 1.5 gallon to liter. 1.89. I'm just going to put in a sub right there. 1.89. I'm going to put in right. SML. Let's call this a min because this is a range. Actually, we can just put this into an array and give it a range of 0.189 to what is 1 gallon, 3.79. Also, I just realized, yeah, it's 1.8, not 0.8. 1.8. We're going to call this target SML range. Okay, so now we've got the range. So our fitness, actually, let's see. We've got the range, but now we've got to figure out how to calculate the amount of water that's going into this thing based off of the frequency and the quantity. So I think the easiest thing for us to do is to probably just create another function, like a helper function here, to determine the amount of moisture. So we can just call this calculate SML. And that's basically just going to be this dot frequency. I guess we should define what the units of the frequency is. So we'll call this per day. No. Per week. Okay. Well, this dot frequency times this dot quantity. And that's going to tell us how much water this thing gets in a week. Yeah. So let's see. Let's weekly water volume equals this. Okay, cool. I guess I need to label the units for this thing too. Oh, why is the tabbing wrong? Oh no. Okay, so this was in liters per week. We also need to calculate for water loss. Let's see, water loss. Water loss is equal to, I guess that doesn't even need to be a variable up here. Let's actually move this down here. And that's a constant, actually. So let's actually name that. Okay. So now we have to figure out how many hours are in a week. Well, I guess we could do the old classic 24 hours in a day times how many days are in a week? 7 times the evaporation rate. And that should give us the amount of evaporation. So now if we just subtract this from the water loss, we should be able to produce the amount of moisture that is in the actual soil. So then we just return likely water volume. I guess it would also depend on the amount of space that the thing has. I guess if we're already here, let's try to figure this out. So before we made the assumption that the surface area is going to be about 0.045 meters per meters squared. So then we need to distribute the amounts of water volume over a certain amount of, I guess, like space volume. So how much space does it take? We're just going to assume that our lettuce is like a cube of about, we said 0.45? Yeah. So let's see. Lettuce volume equals 0.45 times, well, it's squared. How do you square in JavaScript? Math.pow. And the exponentiation operator works too. We're gonna do that. So then the amount of water that goes into the volume should just be divided by the lettuce volume, and that should produce, in theory, the ratio of water to the space. I think that's what we need. Okay, so then the next thing is we just need to find the difference between the soil moisture level and the actual health of the thing. So let's go ahead and just say, what was the amount of moisture that these guys needed? These fellers. Right, so that's the target ratio, or target range. So that actually doesn't go here at all, that goes in here, because this is where we need to actually score it. So we're going to score it based off of whether or not the water is within this range. Let's see, so then the answer of this should be calculate the SML. this dot calculate SML. And if it is within the range, whoop. Oh no. Okay. If this is within, it is less than target SML range 0, then that's bad. But I think it's easier for us to just consider the case where it's actually within the range. Let's see, so let's just do a nice let's actually just do the calculation once. Const SML, this dot calculates SML. Then we just do SML is in range. Oh, so misty. Okay. SML is less than target SML range 1. Let's actually extract that into its own Boolean flag. So the thing that we're trying to measure here is whether or not it's in target SML. We're just gonna yoink. Okay, so then then our Boolean flag should be a lot easier, right? Because it's just if in target SML. I feel like, yeah, we had an extra curly brace there. Yeah, that was an extra one. Okay. So if it is in the target's soil moisture level, then that's good. The fitness score goes up. This dot phi plus equals 1. So what I'm thinking is that this simulation that we're writing here is going to need to run over like, I guess like a few weeks in the simulation time to figure out if the soil moisture level like stays within the range. And then if it does, every time that it's in the range for the week, then we'll just increase the fitness level and roll off of that. Okay, and then we'll just have to make sure that this thing actually grows accordingly. Okay, cool. Man, this is bugging me that this is... Does that work? I don't like it when it's too long. We're gonna abbreviate it to LT for less than target SML. Greater than. Okay, that is a little bit easier for me to read at least. Okay, so the next thing is we should also figure out how we want the water usage efficiency to queue into the fitness function. Well, I guess this is where we use some sort of like a weighted fitness function. So I think it would probably make the most sense if our fitness was something like this. So this is the weighting times phi plus weighting 2 times the water usage efficiency. And so if we have a higher efficiency, which means the ratio of, well, I guess, what is the ratio for this? What did chat say about this? Water usage efficiency versus the growth achieved. Okay, so amount of water versus growth. So then we would probably need to also calculate the WUE, wouldn't we? Calculate the WUE. That would probably, well, this is defined as the water used versus growth. So that should just be this dots oh man, it'd be really nice if instead of us calculating the ratio of whatever, we'll just copy and paste this for now. We don't need that. We do need weekly water volume times the growth. This is just determining, oh, okay. Let's look up how much lettuce grows. Let's ask Google instead of Brave browser. Whoa, 3.5 weeks. Okay, so this is probably measured in, I don't know what the best way for us to scale this measurement is. It does look yummy, doesn't it? We can do like all this like pixel maths. I don't know, how many of these, because this looks like this is the same tray that it grew up in. So how many of those did this thing grow in volume? You want to call that like 50? 100? I'm gonna call this like 100 times. This is impressive. Okay, so let's see. We need to calculate the growth rate. So let's see. The rate was what? It was 3.5 weeks. divided by, no, it's 100 times. I guess from 0.01 meters into 1 meter in 3.5 weeks. So what's the best way for us to model this? Well, I guess this is, yeah, it's just a constant. You can just yoink that and paste it up here. Say growth rate 3.5. The water usage efficiency. Oh, no, ratios are division normally. So this should be a division divided by the growth rates. I think if we were to do this modeling better, we'd probably have to have some sort of function for the growth rate. What function would you use to model the growth of lettuce? Oh. That's a chunky. Okay. I mean, that checks out. The weight of lettuce at the time, the relative growth. You've reached the conversation limit for the day. No! It's okay, we could just refresh this and get a new chat going. I'm going to yoink this though. Well, this seems very handy. Paste that somewhere in our whiteboard. Our handy scratch pad. Paste this somewhere in our sketch. This is example usage, so we just need to hide that. I need just like a nice like mental break right now. I feel like we probably should have picked an easier example. But the idea of modeling lettuce growth is just so funny to me. It's kind of hard to not try to do something with. So we only have like 15 minutes left. Maybe what we can do is, instead of focusing more on the genetic algorithm, since I think other people explain genetic algorithms a lot better than I can, y'all should definitely look at that. But what we can do is we can make this visualization just like have a bunch of randomness to it, just to at least look at something pretty. So what do y'all want to do? Do y'all want to continue hammering out the genetic algorithm? Do y'all want to hammer out some visualization on the lettuce thing? I think I'm going to vote for, I guess, like throwing in some randomization and just like getting these lettuce things to look different. I feel like we've been looking at this for a little bit long. So what we can do is, let's see. I'm just going to throw in some randomness, and we're going to treat that as the lettuce fit thing. So maybe what we can do is we can apply random, and then we need a number range. So we're just gonna have it go from 0 to 100, and then the same thing here, 0 to 100. Okay, that is really busy. So instead of making it pure random, why don't we apply some noise to this instead? Let's see. I have a example of Perlin noise that I was playing with before, and I need to reference how it was done here. Why is it looking so funny? Last time I was toying around with this. There we go. That looks a little bit better. So if you don't know what Berlin noise is, it's just smooth randomness. Basically, instead of it being super random like this, like TV static, the randomness of one value affects the randomness of the value of its neighbor. So if we were to do this here, then it would make it look like the lettuce is growing a little bit more nicely. So let's just see how it was used here. We have the X and the Y, and then we have a scalar here. These things have its own loop, and it's going based off of this. Oop, I've gone too far. So what we need to do is we need, actually, let's just see what happens if we plug in like another number. No. Maybe what we could do is just I don't know. I really don't want to do like a for deep um, for loop just so that we can get a nicer randomness value. Yeah, it's just constantly increasing, huh? So the problem here is that these values aren't in fact increasing. Oh, I forgot that this actually needs to be scaled to 100 as well. That's probably why it's not doing anything. But it's not going to continue doing anything until... It's like a rave party. This thing needs to slow down. Okay, you know what? I now regret I now regret doing this randomness thing instead of just continuing to do the genetic algorithm stuff. We're gonna stop that because that's it's very spammy. I'm gonna chop off the off stuff because that was not satisfying to look at all. It's kind of cool to see the animation though. Crossover. Oh, I didn't even think about like how this was going to, how the genes themselves were going to be mixed. I guess like one way we could mix up the genes is by just having the frequency half be like the frequency and the quantity just be like the two halves of the genes that get mixed up. But I get the sense that this isn't going to actually work properly. Because if we were to look at the example, the text example here, the genes themselves and the DNA was represented as the array of characters. So there's a lot more things that could be kind of like mixed up. And I think if we were to toy around with the other examples that the coding train had, like this one. This one's a really cool example if y'all haven't checked this out yet. Where's the example? Here it is. Let's see how the genes were represented here. The genes were still an array. Maximum strength of the forces. And it was an array of vectors that were influencing the rocket. Okay, and then if we were to go to the ecosystem, how was it done here? This is so cool to look at. Oh, we can spam new things. That's cute. Okay. Um, the way that these genes were defined was just as random points. Why was it random float values? Oh, I think this was in correlation to the speed, because the example made it so that it was optimizing the amount of speed of each loop. The bigger it is, the slower it moves, the smaller the faster. Okay. So this one, the genetic sequence wasn't actually that crazy. For I is equal to, oh, it's less than I. You don't even need this in the loop. There's just two values in it. So yeah, I get the sense that we were going in the right track for creating a lettuce a lettuce genetic algorithm optimizer. I think where was it that we kind of fell off? I think it was just in trying to model like too many things like realistically. I don't know. I'll have to play with this a little bit more for the rest of GHW, and if I end up finishing this, I'll share this sketch in the somewhere in the Discord. But yeah, I guess we only have like 3 minutes left. Thank you so much for tuning in, everybody. Really appreciate the audience. Let me know if you have any questions or thoughts on genetic algorithms. And if you want to do more with genetic algorithms, I do definitely suggest that y'all check out the where is it? The sources over here. Especially this one right here. How did Dan do this? Gets made with neat DNA, but then it is overridden. The genes are so small and yeah, I'm gonna need to take a break and come back to this later. Alright, well. Thanks for tuning in, everybody. I'll see y'all next time, and have a fantastic day. Good luck with your projects. I'll see you later.